Okay, so how do we evaluate the efficiency of inhibitors and how do we compare the efficiency of an inhibitor to another one? Here I have a very simple methods to graph the activity of inhibitors. And so the way we do this is by plotting the velocity of an enzyme on the y-axis versus the log of the concentration of the inhibitors. And by doing that, we obtain a sigmoidal curve in which at increasing concentration of inhibitor, the velocity of the enzyme is decreased until we reach a zero. An important quantity that we can extrapolate from this graph is the log of the IC50. The IC50 is described as a concentration of the inhibitor required to decrease the activity of the enzyme by 50%, so the enzyme rate. The reason this graphing system is very useful is because visually we can easily compare one inhibitor to another. So for example, here we are plotting the velocity of this enzyme versus the log of the concentration of various inhibitors. And we are comparing two of them. So by doing that, we can see that this inhibitor is more efficient because it lowers the rate of the enzyme to zero, basically at lower concentration. And another way of doing that is by comparing the IC50, right, of the two, and we can see the IC50 of the first enzyme is much lower, about order of magnitude lower than the second one. All right, so with that, we have seen a bunch of reversible inhibitors. The ones we'll use in therapy are sulfonamides, protease inhibitors, and other related inhibitors that we'll cover them throughout the course. The second mechanism I want to discuss is the concept of irreversible inhibitors. So this kind of inhibitors also bind at the active site of the enzyme, but upon binding, we have a reactivity with the enzyme itself, and so typically this is because there is an important leaving group on the molecule, and that causes irreversible inhibition by forming a covalent bond between the enzyme and the inhibitor. So note that in this mechanism, we have basically inactivated both the enzyme and the inhibitors in a one-on-one stoichiometric manner. Irreversible inhibitors are orlistat, which is used in the treatment of obesity, antibiotics, so the so-called beta-lactam antibiotics, nerve gases, which are used to inhibit acetylcholine esterase, and others. And as I said, we'll cover these classes of drugs in the second part of the course. So let's look at an example, which is orlistat, used in the treatment of obesity. This drug works by inhibiting pancreatic lipase, which basically breaks down fatty acids in the pancreas and therefore increases the absorption of fat in the diet. So what happens here is orlistat contains a special kind of ester, a cyclic ester called lactone. It also contains a long hydrophilic tail. Binding to the active site of pancreatic lipase triggers opening of the lactone ring by that serine, the nucleophilic serine, and that in turn results in formation of this covalent adduct between the enzyme and orlistat, which is, basically irreversible because it takes a very long time to hydrolyze. So the other class of inhibitors we want to cover is inhibitors that act an allosteric site. And so we cover this kind of mechanism in the first part of this module. What happens is the inhibitor will bind at a site other than the active site. However, binding to this allosteric binding site results in a change in the active site conformation that now prevents either binding of the substrate or prevents the chemistry that was going on between the enzyme and the substrate. Examples of that is a 6-mercaptopurine, which inhibits several enzymes involved in the biosynthesis of purines, and therefore is used as an anti-cancer agent because um, inhibits DNA synthesis. And as we'll see when we talk about anti-cancer agents, that's one of the mechanisms by which we inhibit the proliferation of cells observed in malignancies. Finally, the most interesting kind of inhibitors, which bind actually at the active site, are the so-called transition state inhibitors. Those are drugs that are designed to mimic the transition state of the enzyme catalyzed reaction. Those are likely to bind more strongly than drugs mimicking the substrate of the product. Generally, the difficulty in this kind of inhibition is to identify the transition state of the reaction. Transition states obviously are species that actually don't really exist, cannot be isolated or synthesized, and so we have to come up with analogs of the transition state. So let's look at a few examples. Anti-hypertensive agents that act by inhibiting renin act that way. So there's a pathway that goes from angiotensinogen to angiotensin 1 to angiotensin 2. This is a protein. Angiotensinogen is a protein that is cut by two proteases. First is the renin, which is converting the first part, so to angiotensin 1. And then the second enzyme, ACE, converts angiotensin 1 to angiotensin 2. We can inhibit renin and so block this reaction. So renin is a protease and as such contains two amino acids that we'll see often, to aspartate. What happens is that the protein, the substrate, binds in the active site and basically reacts with the molecule of water present in the active site, which is activated when the aspartate present in the active site. And so what we have is deprotonation of the water, attack on the carbonyl, simultaneous protonation of this oxygen here. And so we form what we call a tetrahedral intermediate with a geminal diol, which in turn then rearranges to give out a new carboxylic acid ending and the free amino terminus of the protein. So inhibitors such as aliskiren somewhat look like the transition states, so they contain this alcohol chiral, and that the rest of the drug basically mimics the peptide backbone that docks in the active site of renin. Other transition state inhibitors are ACE inhibitors, protease inhibitors, such as the ones that we'll encounter in HIV treatment, statins, which inhibit the synthesis of cholesterol. Finally, a slightly different class of drugs still related are the so-called suicide substrates. So suicide substrates work by binding to the active site of the enzyme and then undergoing a reaction. So for example, trifluoroalanine is a suicide inhibitor of alanine transaminase. So what happens usually is that we use pyridoxal phosphate as a cofactor and alanine to carry out this transaminase reaction in which the amine group of alanine is transferred to the aldehyde on pyridoxal phosphate. And so the end result, we have pyridoxamine monophosphate and pyruvic acid. This enzyme can be inhibited by trifluoroalanine, which obviously looks very similar to alanine, and yet contains, these fluorinated groups that have, in part, different properties. So in the reaction mechanism, we have the formation of the Schiff base, just like we did with the natural alanine. Right? So formation of a Schiff base, and then deprotonation of this intermediate, formation of a second intermediate, and then finally breakage of this bond to release the amine on the pyridoxal and the pyruvic acid. So the suicide substrate works very similarly. So the first step, the condensation step, formation of the Schiff base is the same. And then we have the deprotonation step. At this point, though, the intermediate rearranges. And so the difference between trifluoroalanine and alanine is that trifluoroalanine contains a fluorine that can, be used as a leaving group. And so this step rearranges differently. We now form a double bond between the two carbons here. With a nucleophile from the enzyme, this intermediate further rearranges to form a covalent bond between the enzyme and this intermediate adders. So we have now irreversible alkylation, and the enzyme is killed. Okay, so in the last couple of slides, we are covering a few enzymes that are used as targets in therapy. So we have antibacterial agents, typically target enzymes, antiviral agents, anti-inflammatory agents, cholesterol-lowering agents, antidepressants, anti-cancer agents, antihypertensive agents, drugs used like Viagra and Cialis used in the treatment of male erectile dysfunction, anti-gout agents, anti-ulcer agents, Alzheimer's anti-Alzheimer agents, and diuretics. So with that, we have concluded the first part of this module where we have reviewed the use of enzymes as targets in therapy, and we'll move on to talk about receptors.